You know, one of our most powerful weapons in the fight against cancer is, well, it's completely invisible. So how in the world do you aim an invisible force with millimeter precision? Today, we're diving into the incredible, high-stakes science of radiation dosimetry, where getting the numbers right is, quite literally, a matter of life and death. Okay, so let's get right to the heart of the challenge. We're using these incredibly powerful focused beams of energy to destroy tumors. But you can't see it, you can't feel it, you can't touch it. So how do you guarantee that you're delivering a knockout punch to the cancer cells without damaging the healthy tissue that's just millimeters away? This is, without a doubt, one of the most critical calculations in all of medicine. And it all boils down to this really critical difference. On one hand, you've got the intended dose. This is the perfect computer-planned amount of radiation. But on the other hand, you have the actual dose, what the patient's body physically absorbs. The entire field of dosimetry, its whole purpose is to make absolutely certain that those two values are identical, because any difference, even a tiny one, can have massive, life-altering consequences.
So, to see how this all works in the real world, let's kind of shadow a medical physicist. We're going to follow along as they verify the dose for a really common type of cancer treatment. This will take all these abstract ideas and make them super concrete, and you'll get to see the meticulous process that keeps patients safe. All right, so here are the reference conditions. Think of this as the global baseline for these measurements. We're talking about a 6 megavolt photon beam, which is a really standard energy level. The target size is a neat 10 by 10 centimeters, and we're measuring it at a depth of 10 centimeters in water, which, believe it or not, does an amazing job of mimicking human tissue. And our tool for the job? A super-sensitive detector called a Farmer-type ionization chamber. This thing is the gold standard for calibrating these life-saving machines.
Okay, but here's where it gets really fascinating. The very tools we use to measure this invisible force, well, they aren't invisible themselves. They can actually get in the way and interfere with the measurement, creating these tiny errors that physicists have to hunt down and completely eliminate. Let's see how these detectors can, in a way, fool us.
The first major problem has a name, perturbation. And the analogy here is just perfect. Imagine you stick a cold thermometer into a small cup of hot coffee. The thermometer itself is going to cool the coffee down just a tiny bit, right? Which means you get a slightly inaccurate reading. Well, the exact same thing happens here. The physical detector, made of plastic and metal and air, it actually disturbs the very radiation beam it's trying to measure. This is a fundamental challenge they have to solve for.
And what's just incredible to me is how they break this problem down. I mean, look at this. You can see how every single physical part of the detector adds to that disturbance. You've got the detector's outer wall, its central metal electrode, even the tiny pocket of air inside of it. They all add their own little layer of error. So to get to the true dose, physicists have to calculate a super precise correction factor for every single one of these effects. It's amazing.
But it's not just the materials of the detector that are the issue. Its physical size plays a huge role too. And this brings us to the second big challenge, volume averaging. Think of it this way. A detector isn't an infinitely small point, right? It has a physical size. So it ends up averaging the dose across its entire sensitive area. And in a modern, highly sculpted radiation field with super sharp edges, this can kind of blur the reading, smoothing out all the important peaks and valleys and giving you an inaccurate picture of the real dose.
So you're probably thinking, if the detector itself is causing all these problems, how can we ever trust the measurements? Well, the answer is a global gold standard, a rule book that tackles these exact issues head-on. So let's introduce the IAEA's TRS-483 Code of Practice. This is what allows physicists everywhere to speak the same language of accuracy.
The organization behind this is the International Atomic Energy Agency, or the IAEA. Their whole mission is to promote the safe use of nuclear technologies. And by creating these incredibly meticulous documents, like TRS-483, they provide a standardized framework. It ensures that a patient in a hospital in one country receives the exact same safe and accurate dose as a patient anywhere else on the planet.
Okay, so how does this rulebook actually work? I mean, how do physicists use it to get from some raw number on a screen to a dose that they can be absolutely 100% certain about? Let's get into the calculation and see how this all comes together.
The whole thing can be broken down into 4 key steps. First, you start with the raw readings straight from the detector. Easy enough. Next, you have to correct for things in the room, like air temperature and pressure. Then comes the really big one. You apply a whole series of complex correction factors for the specific beam and the specific detector you're using. And only then, finally, do you get the true absorbed dose to water. That's the number you can trust with the patient's life.
Now, of all those corrections, the most important one is called the beam quality correction factor, or KQ. The best way to think about it is like a translation key. You see, no two radiation machines on Earth are perfectly identical. This factor essentially translates the reading from the perfect, idealized beam at a national standards lab where the detector was first calibrated to the real-world clinical beam that's being used on a patient right now. It corrects for all the subtle energy differences, tailoring that measurement perfectly to the machine in that room.
But here's the thing. Getting an accurate dose at one single point right in the center of the beam, it's just not enough. Not anymore. Modern treatments use these incredibly complex, sculpted radiation fields that are designed to match a tumor's exact, weird shape. To really understand the dose and calculate the right corrections, physicists have to see the full picture. And that's exactly why they measure something called a lateral beam profile. What they do is they physically scan the detector across the entire beam, from one side to the other, basically mapping out the dose. This profile shows them the beam's exact shape and, crucially, the sharpness of its edge. And here's why that's so important. The data they get from these detailed profiles is exactly what they need to accurately calculate and correct for those blurring effects, like the volume averaging we were just talking about. And get this comparison shows why the energy of the beam matters so much. On the left, you've got a higher energy 18 MV beam. On the right is the 6 MV beam from our case file. Do you see how the 6 MV beam creates much sharper peaks and deeper valleys? That means it can be sculpted with way more precision to match the weird, irregular shape of a tumor. It's a perfect example of how higher energy isn't always better. When it comes to this kind of work, control is everything. So, okay, we've walked through some really complex problems and the elegant, meticulous solutions that physicists have developed. But let's just take a step back and really focus on the stakes here. Why does this unseen science, this obsession with decimal points and correction factors, why does it truly matter?
This graph says it all. This shows what the world was like before these standards were widely adopted. You had different hospitals, all measuring the exact same radiation field, and they were getting wildly different results. The data shows a spread of almost 15% in their measurements. Look, in radiation oncology, a 15% error isn't just a mistake on a spreadsheet, it's the difference between a successful treatment and a tragic, catastrophic failure. This is the chaos that standardization prevents.
And this isn't just some abstract theory. I want to read you a quote. This is directly from the IAEA report itself. Quote, "The use of inappropriate detectors for measuring field output factors without further corrections has been reported as the main cause of an accidental overdosage of patients." It just doesn't get any clearer or more serious than that. Getting this science right directly physically prevents people from being harmed.
So, here's the crucial point, the main thing to take away from all this. Every number, every correction factor, and every single meticulous step is part of this global system of checks and balances. And it's all designed to ensure one thing, that the right dose is delivered to the right place every single time. That is the unseen science that makes modern cancer therapy both possible and safe.
It really makes you wonder, doesn't it? What other invisible, high-stakes calculations are happening all around us, every single day, quietly keeping our world running and keeping all of us safe? Thanks for tuning in.